Okay, so now let's look at the fourth notebook, and here we'll resume a discussion of Matplotlib. Okay, slightly more complex plots now. So we'll first import Numpy as usual as np, and we'll also import matplotlib.pyplot as plt. Okay, right. So what we're going to do now is look at three plots, three kinds of plots. One is a bar plot, another is a histogram, and the third is a scatter plot. But then we will introduce these not suddenly. Okay, so what we will do is we will look at them in context of probability and statistics. Okay, so what are we going to do now? We are going to look at how we can sample from probability distributions. Okay, different probability distributions, and once we have sampled a set of points from a probability distribution, then we can visualize this sample of data points using different plots. Depending on the nature of the distribution from which we are sampling, the kind of plot will also change. So the first question therefore is, how do we generate random numbers? So we can use a utility called a random number generator. So this won't exactly give you random numbers, so to speak. They'll be pseudo random. Okay, so you can have some control over the randomness. It will appear random, though in principle it is not exactly random. Okay, so such numbers are called pseudo random numbers, and NumPy gives us a way to generate these random numbers. So there is a module called random, np.random. Okay, and there is a random number generator that we will make use of. So this is how we generate. We get hold of a random number generator, default underscore RNG. So we call this RNG. Okay, so what can we do? Let's try to generate some random integers. So let's say between 0 and 5. This is going to generate some random number between 0 and 5, where the endpoint 5 is not included. So maybe we can include the endpoint. I'm going to pass an extra argument and say that endpoint equal to true. So what is this doing? Let me separate this into a new code cell. This is, so whenever I run this, it's randomly generating a number between 0 and 5. Okay, it could generate 5 also. That's why the endpoint is true. So you see that every time I run it, I get a different random number. So let me keep running until I get a 5. Yeah, so I got a 5, right? I got 5 2 times, in fact, succession. So what is the distribution governing this? So this is actually uniformly randomly generating numbers between 0 to 5. So if you think about it, the probability of obtaining any single number would be 1 over 6 in this case, because it's 0 to 5. Okay, so that's how you generate a random number. Now when you're using randomness in some of your experiments, be it in machine learning or some other discipline, you might want your results to be reproducible. So you have used randomness in your experiment, but then when you are presenting it to someone else, you might want to have some control over the randomness. So that is achieved using this concept called a random seed. So you have np.random.default underscore RNG. Now you can specify what is called the seed value. So if I specify some seed value, it's some integer, right? In this case, I'm specifying 42 as the seed value. Now let's generate some, say, 10 random numbers between 0 and 5. Okay, so the size equal to 10. So I'm generating 10 random numbers uniformly between 0 and 5. Okay, I'm sampling them. So let me run this. Now I'm getting this sequence 0, 4, 3, 2, 2, 5, 0, 4, 1, 0, right? Now let me run this again. Notice what happens. I am getting the same sequence 0, 4, 3, 2, 2, 5, 0, 4, 1, 0. No matter how many times I run this, I will get the same sequence of random numbers, right? Pseudo random numbers. So that is the power of the seed value. So once you set the seed value, you have some control over the kind of numbers that you would see. In fact, they will be exactly the same. The sequence of numbers that you would see will become deterministic. Okay, but on the face of it, it's still random because you won't keep fixing the seed value for every cell. Okay, so usually what will happen is, if you're running an experiment that requires randomness, you will fix the seed value once, right at the beginning of the code, and then you will continue the experiment. Maybe if you want to run multiple runs of the experiment, for each run of the experiment, you might change the seed value, but you won't keep changing the seed value for every cell in your notebook. Okay, so that's something that we should keep in mind. Now let me run this without a seed value and see what happens. So notice that every time I run it, I get a different sequence of numbers. Okay, so that's regarding the seed value. So let's look at. So I already mentioned that rng.integers between some start point and some end point. If you set endpoint is true and say size equal to 100, this is going to generate 100 numbers uniformly at random between 0 to 10. Okay, the probability will be 1 by 11 in this case of seeing any given number. Okay, so what about, yeah, so one point before we move on. So does that mean that out of 100 numbers that I generate, 100 by 11 sorry, 100 by 11 will be 5 and 100 by 11 will be 2, the number 2 and so on? No, right? So you have to understand that the probability is 1 by 11. Okay, which means if you repeat the experiment several times, okay, in the limit, the number of times, let's say a 5 appears, divided by the number of times you run the experiment, that will approach 1 by 11. Okay, so you have to keep in mind that in any sample, in any finite sample, you won't have exactly the sample size divided by 11 number of data points, right? So that's not what you're going to observe. But what you will see is that as n becomes large, the fraction of 5s or the fraction of 4s will approach the corresponding probability. Okay, so this is something that you must know from your stats courses. Okay, so that's the discrete uniform distribution. Now you can also generate continuous uniform sample from the continuous uniform distribution. Let's say we are sampling for numbers between 0 and 3. Okay, and the size equal to say 10, right? So 10 sample size is 10 and you are drawing uniformly in the range in the interval 0, 3. Okay, so we have seen how to sample numbers from distributions, the uniform distribution to be specific. Now what we'll do is we look at the Bernoulli distribution, right? So RNG, the way to do it, so earlier we have looked at uniform, we have looked at integers. Now we look at another method. This is called choice. Okay, very versatile method. So think about this as flipping a coin. The coin has heads and tails, right? So heads is, let's say, 1, tails is 0, and the probability of heads is 0.7. So I need to specify the probability of each of these two possibilities, right? So this is 0.3, 0.7. Okay, that's your probability. And now I want to generate 1000 samples. So size is 1000. So I want to toss the coin 1000 times. So the result, let's call it x sample, and this is how x will look like, right? So it's a bunch of zeros and ones. What is the shape of x? It's 1000. Now how do we visualize this in the form of a plot? So you can do what is called a bar plot, right? So plt.plot, plt.bar, the x-axis, on the x-axis you will have 0 and 1, and on the y-axis you need the counts, right? You need to know how many times tails occurred and how many times head occurred. So you want the count. How do you get hold of the counts? So there is this utility in Python. From the collections module you can import what is called a counter. Okay, so what does counter do? If you pass x as input, let's see what counter returns. Counter is going to give you the frequency of occurrence, right, of the individual element. So remember that x is an array of zeros and ones, and 1 occurred 702 times and 0 occurred 298 times, right? So that's very convenient. So if you can call this the frequency, right, and if you use freq 0 and freq 1 is like a dictionary, right? So that will give you the frequency of occurrence of zeros and ones, and that's exactly what you want if you want to plot a bar plot. Okay, so now this is plt.bar, and what you have is two bars. This is left bar is 0, right bar is 1, but on the x-axis you still have something that you don't want to see, right? So you don't want something that's continuous. It's discrete, right? 0 or 1. So you can control that using x ticks. Okay, so the x ticks, if you specify it as 0 and 1, then you'll end up with the 2 bars. Okay, you can suppress this unwanted output, and that will give you your bar plot. So roughly you can see that the probability of seeing the heads, roughly estimate, this is an estimate, right? You can estimate that probability of head falling, that's about 700 by 1000, 0.7, and naturally the probability of tails is 0.3, right? So the underlying story is that you can use bar plots to visualize something like this, right? So something that's discrete and you have a frequency for each item, you can visualize them using a bar plot. Okay, so some other instances where you might use a bar plot is you have the grades of students in say MLT course, right? So there are 1000 students and they have obtained grades all the way between U and S. So S, A, B, C, D, E, U, so that will be 7 grades. So you will have 7 bars, and the height of the bars will correspond to the frequency or number of students who have obtained that particular grade. Okay, right. So next we go to the normal distribution. So let's get rid of some rendering issue. So I'm going to put it this way. Yeah, so now we are going to sample from the normal distribution with mean 1 and variance 4. Okay, so where would you encounter something like the normal distribution? Marks of students, right? Or the height or weights of people in the room, right? In this case, let's think about it as the marks of the students who have written an exam. So the mean mark could be 50, and there could be a deviation of standard deviation of 2 or variance 4. Okay, and you want to sample 10,000 points from this distribution. So you have RNG dot normal, okay, and you specify the mean and the standard deviation and the number of samples. So in this case, there are 10,000 samples, and that's all there is to it. So if you know sample, you get an array of shape 10,000. Okay, now what we'll do is, you might wonder, so while working on these problems, you might get stuck at certain stages, right? So for example, I am confused or I'm doubtful whether this corresponds to the standard deviation or the variance. So what I can do in such instances is to actually go and ask for help. So if you name the method here, in this case is the normal method, and add a question mark and run the cell, that will give you help on the right hand side. So in this case, I can see that you are drawing, this is helping you draw normal samples, and this is the center, this is the standard deviation as expected, right? So whatever I've done is right, so I should enter 2 or not 4. Okay, and then there is size, so that's the third argument, and size is 10,000. Okay, so it's a useful command that you can keep in mind. So that's X. So what can we do? How do we visualize this sample? I can plot a histogram. So the way you plot a histogram is plt.hist. Let me first give in X as the argument. Okay, this is what you have. Now this doesn't look so good. So what I'll do is, there are a few more arguments that you can add. First is the bin sizes. So I'm going to add 10 bins. Suppress the output. By default, I think it's 10. So maybe let me change it to 20. Okay, it's to show you the difference. So you can see that the number of bins are changing, but it's still not, the bin separation is not quite clear. So I'll add what is called the edge color. I'll make it black. I'll make the edge color black. So the bins are now going to be well separated. Okay, so you can see that the bins are now clearly visible. Let me go back to 10 bins. Now let's move on to another case where we are now looking at a bivariate Gaussian, or a normal extension of the normal distribution to 2 dimensions. So it's a bivariate Gaussian. Now where would you encounter something like this? You have seen this in ML, right? You have seen this in, say, the Gaussian naive Bayes case, where you have the class conditional densities being given as bivariate Gaussian. So that is one instance where you might have seen this. More concretely, you could think of this as the landing map of balls on a cricket pitch, right? In a given match, so they'll all cluster around some region on the cricket pitch, right? So you could think about it that way. Anyway, so what we need to do now is, we have the mean. So this is an array of 1, 2 is the array, and we have the covariance matrix, right? So that's the covariance matrix that's sitting there here. So that's actually a 2D NumPy array. It's a matrix. So what is it? It's 1 0. It's a diagonal matrix. In fact, since it's a diagonal matrix, let's specify it as np.diag. Okay, 1 comma 5. It need not always be a diagonal matrix, but in this case it is. And what are we trying to do? We are trying to now draw samples from a bivariate Gaussian. So RNG has a method called multivariate Gaussian. Okay, it's a generalization of the bivariate Gaussian. So you have to specify the mean, you have to specify the covariance matrix and the size, number of samples. So 1000 points. Okay, that will give you the samples, right? So let's now see what it is, what happens. Sorry, so we made a mistake here. This is okay. So RNG dot sorry, this is RNG dot multivariate normal, not the Gaussian, right? So this is once again the help function is helping me here. Okay, what is also helping me is the autocomplete. So RNG dot, I entered MUL and then I pressed a tab. Okay, so then I realized that it's multivariate normal and not multivariate Gaussian. Okay, so let me go back. It's multivariate normal. Okay, so what is the shape of X? What do you expect it to be? It's 1000 comma 2. So remember that you're sampling 1000 points, but each point is going to be in R2. Okay, so now you have to visualize them. How do we visualize them? We can do what is called a scatter plot. We have already seen scatter plots. So first I give the X coordinate and then the Y coordinate. So what is the X coordinate? X coordinate is in the first column. Remember that there are two columns in this matrix. So I need a column size. So this is how it's going to be. This is a scatter plot. Okay, so now sometimes scatter plots can be deceptive because of the scale. Okay, it looks as though the data cloud is spherical, but in reality, notice that most of the variance is along the y direction. Okay, there's a phi in the variance along the y direction is phi. Of course, not the sample variance, but if you look at the covariance matrix of the underlying distribution, most of the variance is along the y direction. So this is not really spherical. It should look more elongated along the y-axis. So how do you fix this? You set the axis as equal. Currently they are not equal, but then you set equal aspect ratio for the axis, and when you do that, you get what you're looking for. Okay. So one more thing that you can control when you do scatter plots is to make the data points more transparent. There is a parameter called alpha that controls the transparency of the data point. So alpha equal to 1 is completely opaque data point. So if 2 points coincide or overlap, you won't know really what's happening. So it's totally opaque, right? But if you make it 0.5, let's say, now you notice that you can discern overlapping points, right? And if you make it 0.1, you are making it more transparent. So this kind of gives you a sense of where the points are clustering. Okay, so notice that they're clustering around the mean. The mean is what, 0 0, right, as we expect, or rather 1 comma 2. So there isn't enough resolution here, so this is somewhere around 1. Okay, yeah, it's 1 comma 2, right? So 1 comma 2 is where they are clustering around, and there you see that there is greater density, and as you go away, the density of the points or the number of points come down. Okay, so these are things that you can control in a scatter plot. So finally, let's look at this idea of a Gaussian mixture model. Now it's a mixture of Gaussians. So what we are going to do is we are going to combine all the things that we have learned so far and come up with the distribution of this GMM. So what is n going to be? Let's look at n is nothing but the number of samples. So I want to sample 1 million points from a GMM. Okay, so how are we going to do this? So we can think about this as a two-step process, right? First, we are going to choose one of the three. There are three mixtures. So we are going to first choose a mixture, okay, and then we are going to generate a point from the corresponding Gaussian. Okay, so how is that going to work? We have to choose 1 million points, right? and there is a we have to come up with 1 million choices for Gaussian to choose. Okay, so there are three choices, either it's the zeroth Gaussian or first Gaussian or second Gaussian. Okay, so this is what we have, and we have to choose them in a certain probability, right? So what are the probabilities associated with these three mixtures? P equal to 0 0.2, 0 0.3, 0 0.5. Okay, so we have to choose from 0, 1, 2. Okay, with this probability, how many points? N points. Okay, so let me pull this here. So what will this give us? This will give us 1 million choices. Okay, so let me run this and see what. Let's look at choices. So what is, say, the first 10 choices? What are they? For the first point, I have to sample from the first Gaussian. For the second point, I'll have to sample from the zeroth Gaussian, so on and so forth. Okay, so now for the samples, the actual samples, right? There'll be how many number? 1 million. So let me initialize this with set of zeros. Okay, n zeros. Okay, so this is an array of size 1 million. Into each component or element of this array, I'll have to put in one of the samples drawn from the corresponding Gaussian, which I will pick from choices. Okay, so that's the idea. So now I loop. Okay, so here I have to loop. So let me, for I in range of n, what am I going to do? I need to fill in x of I. I need to draw a sample x of I. Which Gaussian will I choose? So first of all, it's a Gaussian. So rng.normal. What will be the mean? Okay, so the means are given here. So I'll have to probably fill that in. So the means are, let me call it mu's. So this is np.array of, what are they? 10, 15, 18. And they all have unit standard deviation, so I don't need to worry about that. So what is the choice? The choice is choices of n. This is the choices of I. So this is the Gaussian, the index of the Gaussian that I have to choose. Okay. Now, what is the mean? Use of choice. Okay. So choice will be 0, 1 or 2. Corresponding mean will be drawn from use of choice, right? So this, with this mean and with a standard deviation of 1, give me one sample. So that is x of I. Okay. Now if I run this, I'll end up with my sample drawn from my GMM. Okay. So I will have 1 million of them. Now what I can do is I can go ahead and plot a histogram with x. Okay. Once again, the number of bins, let me say make it 1000, and edge color, make it black. Suppress the output and see what I get. Okay, there you go. So that's your distribution of samples drawn from a GMM. So notice that the means are 10, 15, 18. So therefore there's a very clear distinction between 10 and the remaining two Gaussians. The other two Gaussians, since their means are close together, are kind of mixed together. Okay, but yeah. So this is the end of the collab on sampling from distributions and then using them to visualize and then making use of them to understand bar plots, histograms, and scatter plots. Thank you.